Is it possible that a system can get overwhelmed by having too many IKE Phase 1 negotiations going on at any given time? The answer is absolutely yes. We have a control that can help mitigate that risk, and it has a title named Call Admission Control for IKE. Let's jump in. A very well-known attack is called the TCP SYN flood attack. And let's say we have the attacker out here, and we have a firewall of some type, and then we have a server on the left. And what the attacker does, it initiates a TCP SYN request to the server, and of course that server is going to answer with a SYN ACK back, and then the attacker doesn't follow up with that third part of the three-way handshake. Now the attacker using a single TCP SYN request with one SYN ACK coming back is not a big burden on the server, although the server may have to maintain some state information regarding that half-formed TCP session that's in place. But to amplify this, the attacker could send in hundreds or thousands of these TCP SYN requests, all looking like different sessions to the server, and in a distributed denial of service attack, we might have tens of thousands of devices all sending in multiple TCP requests to the same destination. And to be a little bit more malicious, we could spoof the source addresses so the server is trying to reply back to somebody else. And by so doing that, now we're interrupting other people's devices and networks. In addition to this victim, we now have a second victim. Now, because TCP SYN floods are so well known, we do lots of things like on the firewall, we set up limits for the maximum number of half-formed TCP sessions that can be sent through. And we can set up those limits per host. So we can say, for example, only so many half-formed sessions to this host. And we can also limit the number of full TCP sessions that are fully established to a single host. The firewall can also step in, and it can actually do a proxy for that three-way handshake and take the brunt of that abuse. Instead of passing on those sessions to the server, the actual firewall could go ahead and respond with a SYN ACK, and then if a valid client came in and finished off that three-way handshake, then the firewall could forward that to the server as a valid TCP session. And the firewall also may use things like TCP SYN cookies, so it doesn't have to maintain the state of all those half-formed sessions, which lessens the burden on the firewall as well. Now you might ask, Keith, why do you bring up a TCP SYN flood attack? How does that relate to IPsec? Well, in our DMVPN and in other implementations of IPsec, if we're using IKE version 1, we have phase 1, and we also have phase 2. And in phase 1 of IPsec, if we're initiating a tunnel, we're going to have negotiations. And for the negotiations, we're going to haggle, hashing, authentication, Diffie-Hellman group, lifetime, and encryption. And then after the negotiation's done, we run Diffie-Hellman based on the group we agreed to. And then after that, the third step of IKE phase 1 is the actual authentication itself, based on what we agreed to in the first part of IKE phase 1. So let's imagine this hub or any of these devices that are going to be accepting inbound IKE phase 1 requests from another device. Because when R2 cuts over to R4, or R2 cuts over to R3, or R3 cuts over to R4, the potential is we could have a full mesh of IPsec sessions. Now what if the attacker, I'll go ahead and put the attacker right here, these guys are friends. What if the attacker says, hey Mr. R3, I'd like to go ahead and start an IKE phase 1 tunnel with you. So they go through the negotiations, they go through Diffie-Hellman, they go through authentication, and maybe the attacker doesn't have the pre-shared key, but guess what? We have just consumed a whole boatload of resources here on R3. The IKE phase 1 processing, the negotiation, and the Diffie-Hellman, that takes a whole bunch more effort than a single TCP session being established. So if the attacker can send in multiple IKE phase 1 requests to R3, or we have a botnet with thousands of devices, all trying to do an IKE phase 1 tunnel negotiation with R3, it's very possible that we could consume all the resources on that spoke. To mitigate this risk against any of our devices that are part of the DMVPN, we can use the crypto IKE call admission control and set the upper limits as far as how many sessions we're willing to have on any given device at any time. And that's what the SA limit is all about. And it's specifically for IKE, meaning IKE phase 1. So in our topology, let's say worst case, we have 2 IKE phase 1 tunnels between each device and every other device. And it's not likely that we're going to have that many. So using this as an example, if we thought, okay, each device at any given time should have no more than 6 IKE phase 1 security associations in place, we might set the SA limit to like for 10. Because all we're really trying to do is we're trying to limit a denial of service attack from an attacker who's bombarding us with hundreds or thousands of IKE phase 1 negotiation requests. Setting this limit also is going to protect us against some malformed system or a system that's having a problem. Maybe we have a router that's over and over again trying to set up new connections to the hub based on a logic error or some problem with the software that's running. The other thing we'd want to take into consideration is what if we have this router right here also acting as a VPN server for remote access? Because if we're using IPsec remote access VPN tunnels as well, we're also going to need IKE Phase 1 tunnels for that traffic as well. So taking the remote access out of the picture just for a moment, we might want to set this limit here to 10 per DMVPN device. And we can set the in-negotiation limit as well to 10. Now, if we set the in-negotiation limit, that doesn't apply to the final hard limit on the actual IKE Phase 1 tunnels. So these numbers don't have to be the same. For example, we could set this to 7, which would mean on the router that we apply this to, it's okay for me to have 10 IKE Phase 1 security associations. However, at any given time, I'm only going to allow the negotiation of up to 7 tunnels. So in a sense, this is kind of like rate limiting our IKE Phase 1. So what you and I get to do here in just a moment is we're going to implement this. It's very, very simple to implement. And I did make a little bit of a topology change. I wanted to share that with you. I changed these interfaces from gig 1/0 on each of these interfaces that are facing the internet, and I swapped them out with serial 1/0 for all these interfaces respectively. So only the type has changed, not the number. And let me share with you why I did that. I have these routers emulated inside of GNS3. And one of the huge benefits is that we can do a packet capture in this virtualized environment and pick up the packets right on the wire, put them right into Wireshark, and see exactly what's happening, which is a huge benefit for learning and troubleshooting. And the big reason that I swapped out the gigabit interfaces for serial in my virtualized environment here is because with the version of iOS that I'm running and the interfaces that I was using, I was getting too many IPsec errors, like malformed frames and such. So I was doing packet capture and verifying. Sure enough, I've got these malformed packets. So as part of the troubleshooting, I had several options. It reminds me of a story about this group of people that were in a car, and they were driving down the road, and the car got a flat tire. Now, the 3 people in the car, there was a computer salesperson, there was a programmer, and a technician. So they pull the car over to the side of the road, and the technician says, hey, you know what? Let's just replace all 4 tires, and that'll solve the problem. And that's effectively what I did here. I replaced these 4 interfaces with serial, and haven't had the problem since. And the reason I pass it on to you is that if you're doing this in a virtualized environment, and if you're having sporadic IPsec issues or errors, one of the quickest fixes is to swap out all 4 interfaces that were connecting these devices together, and that has solved the problem in my topology. Now, the computer salesperson in this car said, you know what, let's just buy a new car. That'll fix the problem too. And it would. And the buy a new car option would be, for example, tearing down the entire topology and building a whole new, completely different one. Maybe different versions of iOS or a different emulator, or moving to a physical environment or a different virtualized environment. And the third person in the car was the programmer. And the programmer said, you know what? Let's just turn off the car, start the car again, and pull out on the freeway, and maybe the problem, which was the flat tire, maybe the problem will just go away. Because we all know how a good reboot sometimes fixes things. However, this topology is having those sporadic errors. And it wasn't all the time. It was just periodically. It was bothering me. So I swapped them out and haven't had the problem since. The other question I get quite a bit, so I'm going to answer it while I'm right here as well, is how do I build this topology? And the answer is I've got one router right here in the middle. It's R5. And it simply has an interface that goes to R2, has an interface that goes to R1, R4, and R3 respectively. So R1, R2, R3, and R4 all have a default route that says send the packets to R5. And then the overlay of DMVPN and the IPsec and the routing on top of the GRE tunnels does all the rest of the magic. Also, in a practice lab, I use a numbering convention that's very easy to remember. So the last octet of all these routers matches the router number. So R2 ends in .2, R4 ends in .4. So on this link between R4 and R5, R5 would have the address of .5 on each of these interfaces. And the number 15 actually to me means from router 1 to router 5. The network 25 to me means router 2 to router 5, and 35 and 45 respectively. So in the real world, we're not always going to have a chance to pick our exact correct numbers that we want to use for addressing. However, in a lab environment that you completely control, I strongly recommend that you practice some kind of a numbering convention that will assist you in remembering where things are as you practice and learn the technologies that you're applying in your practice environment. Let's do a quick check here on R2, one of our spokes, just to verify that our routing is in place. If the routes show up, that also implies that the DMVPN, the IPsec, is working as well. From R2's perspective, it does have a route for the 10.44 subnet, which is down here. We're sitting at R2. It sees the next hop as 172.16.0.4 out of its multi-point GRE tunnel interface. If R2 does not yet have a mapping for the next hop of 172.16.0.4, which is the GRE interface on R4, and traffic is trying to go to that network, R2 will send the first packets through the hub. It will also send an NHRP request in the direction of the hub to find out what that non-broadcast multi-access address is of R4, so that R2 can build that connection directly between R2 and R4. So let's do some pings. Let's go all the way around the horn. Let's ping 10.1.1.1, which is behind R1. We'll source it from our gig 2/0 interface. And the gig 2/0 interface is the interface that's connected to the local 10.2.2 network here on R2. So that packet was sent to 10.1.1.1, which was the IP address of R1's interface on this network. And it was sourced from 10.2.2.2, which is R2's IP address on its 10.2.2 subnet. And that works great. Next, let's go ahead and ping 10.3.3. That's the subnet that's sitting behind R3. And we'll also source that from our local 10.2.2 subnet. And that is working as well. So the first packet, if NHRP resolution had not yet been done, would have gone through the hub. And after NHRP, the subsequent packets would go directly between R2 and R3. And when that cutover happens, that will also trigger the IKE phase 1 process between R2 and R3, which would be followed by the IKE phase 2 to build the IPsec SAs between those two devices. Next, we'll do a ping over to 10.4.4.4. We don't want R4 to feel left out of the party. So just to verify I got all three of those, we'll do a show history. And sure enough, we've done a successful ping to all of the remote subnets, which also means that we should have at least one IKE phase 1 tunnel between us, R2, and every other device. And for the spokes, it's very possible that we'll have a couple, because both spokes initiated their own IKE phase 1 tunnels, and so we have a pair of them. Now, I'd like to ask you a question. What command should we use right now if we wanted to just see the IKE phase 1 security associations? Now, there's a couple commands we could use. Which one comes to mind? I'd like you to think about that for a second. And the one that I'm thinking of is the show crypto isokemp SA. Please just show me the IKE phase 1 tunnels that are currently in place. So if we look at these tunnels, this one right here is between R1 and R2. So that's 1001. This tunnel right here, which is tunnel 1002, is between R2 and R3. This tunnel right here is also between R2 and R3. There's 1003. And tunnels 1004 and 1005 are right here. So 1004, 1005. And if we look at the source and destinations for those tunnels, and you'll notice if we take a look at the source and destinations for those, that for these two tunnels, R2 initiated one of them and R3 did the other one. And for the tunnels between R2 and R4, R2 initiated one of them and R4 initiated the other. So on R2 at this very moment, we have 5 active IKE phase 1 security associations. Now we haven't administratively come in and set any limits for the number of IKE phase 1 tunnels. But we can see what the defaults are with the command of show crypto call admission statistics. So by default, it's saying, you know what, 1,000 IKE phase 1 tunnels being negotiated at any given time is the maximum I'm willing to do. And that's a pretty high number, 1,000 of actively negotiating IKE phase 1 tunnels. So in our clipping with call admission control, we can set that to something lower. And we can also set the number of maximum IKE phase 1 tunnels that can be established. The default of 0 implies that we're not limiting it yet at all. Now currently we have 5 security associations for IKE phase 1. If we went in right now and said, okay, the maximum number is 3 as an example, or the maximum number is 2, it's not going to affect any of our existing IKE phase 1 security associations. They're already established, they're already in place, they're already set, but what this will do, this will affect any new IKE phase 1 tunnels from being established. Because once we're at this number that we set as the maximum, or in our case, higher than that number, any new connections won't be allowed. To set the upper limit for the maximum, we simply go into configuration mode, and we're going to use the command crypto call admission limit IKE SA, and then the magical number that we want. In this case, we're going to set it to 2. Now we have this beautiful syslog message that's saying, hey buddy, you currently have 5 security associations in place, and now we're setting this limit to 2. If you want any new IKE phase 1 tunnels to be established, you've got to drop below the number of 2, like for example 1 or 0, in order for me to allow those new connections to come in place. Because going forward, as far as any new IKE phase 1 tunnels, the maximum number is 2. So the existing sessions are perfectly fine. They're not going to be torn down because of this command. However, in the future, if we ever try to go above 2 IKE phase 1 tunnels, it's not going to happen on this device. The other number that we can set is the maximum number of IKE phase 1 negotiations that are currently going on at any given time. Now this number is separate from the total number of established SAs, and this can help to rate limit the number of active IKE phase 1 negotiations that are happening at any given time on the box. And the syntax for that is crypto call admission limit IKE and the keyword in-negotiation-SA and then the number that we want to set the limit to. and the minimum number is 10. So previously, by default, it was willing to do negotiations simultaneously for up to 1,000 IKE Phase 1 tunnels, and now it's limited down to 10. If we wanted to verify that, we could simply do a show crypto call admission statistics like we did earlier, and now compare the differences. So now we have a number of maximum IKE SAs that we can set up is 2, and the max number for negotiations is 10, based on the parameters we specified here and here for call admission control. So to confirm that we haven't lost any of our IKE Phase 1 security associations, we can do a command of show crypto ISAKMP SA, and lo and behold, we should have the exact same 5 SAs in place. However, any new SAs won't be allowed because we're over the limit of 2. Now, in order for CAC to be seen in action, we need to create an additional SA. So to do that, let's go ahead to each of the routers. We'll start with R1. We'll go into interface configuration mode for serial 1/0, and we're going to do a shutdown. I'm also going to issue a command clear crypto ISAKMP and clear crypto SA. That should remove any possible IKE Phase 1 and IKE Phase 2 tunnels that are active between R1 and the rest of the world. And we just lost our 3 neighbors. I'm going to do that exact same treatment on R2, R3, and R4, just shutting down the interfaces and clearing the security associations. Next, we're going to go to each of those routers again and simply bring the interface back up. So here on R1, interface serial 1/0 is up. We'll go to R2, do the same thing. Go to R3, similar treatment. And then finally, R4, we'll bring that up as well. And in just a few moments, each of the spokes will have registered via NHRP with the hub. They'll have established their IKE Phase 1 and IKE Phase 2 tunnels with the hub. And back on R1, we should see 3 new adjacencies. And there's the third one. Okay, great. So that implies that our spokes have all checked in and successfully negotiated with the hub. So let's make a road trip over to Mr. R2. And on R2, let's go ahead and do a show crypto ISAKMP SA. And I'm expecting we're going to have 1 IKE Phase 1 tunnel between R2 and R1. If we did a show crypto IPsec SA, we would also see the IKE Phase 2 tunnel information between R2 and R1. However, our focus right now is on the call admission control for rate limiting and controlling the maximum number of IKE sessions. So currently, we have 1. Now let's also verify that we have our routing in place. Let's take a look at our EIGRP learned routes, the show IP route EIGRP. And just to verify reachability, let's do a ping over to 10.1.1. And that looks successful. We use the up arrow key a few times and do a show crypto ISAKMP SA. We still have that 1 IKE Phase 1 tunnel between R2 and R1. However, if we start pinging over to 10.4.4, then NHRP is going to kick in. We're going to resolve the neighbor's NBMA address. We're going to build a connection straight to R4. And that will require another IKE Phase 1 tunnel as well. So to test that theory, let's do a ping to 10.444. We'll source it from our 10.2.2.2 interface. And that's working as well. And we have this beautiful console message saying, hey, sorry, I'm denying one of your IKE Phase 1 sessions because you're already at your limit of 2. So what happened here, the NHRP request went down to R4. And it's very likely that R4, in connecting up to R2, was the first one to negotiate an IKE Phase 1 tunnel. So it's very likely that that IKE Phase 1 tunnel was the second one. So our first one was right here between R1 and R2. And the second one was between R4 and R2. And the one that it's denying is trying to go from R2 over to R4. That would be the second or redundant tunnel, if you will, for IKE Phase 1 from R2 to R4. So we could verify that. We could do a show crypto ISAKMP SA once again. And sure enough, this tunnel right here was initiated by 45004. That was R4 going to us. It's established. It's QM idle, which is perfect. And it's working. However, when we tried to initiate our IKE Phase 1 tunnel, a new one, back to R4, that's when CAC kicked in and said, sorry, buddy, you're at your max. You're at 2. That's all you get. If we issue the command show crypto call admission statistics, as we have previously in this video, it'll go ahead and give us the details regarding packet counts. So as far as rejected IKE request, we have 1 that got rejected. We're currently set for a maximum of 2. We're currently at 2. Our maximum for negotiations is at 10. At the moment this command was issued, we had no current negotiations in progress. Now the sad news and the funny news is this. If we tried to do a ping now, for example, over to 10.3.3.3, we would also do the NHRP request trying to resolve this address, and we would also try to build this GRE connection between R2 and R3. But because the call admission control says, hey buddy, you're already at 2, you don't get any more IKE Phase 1 tunnels, R2 will not be able to successfully establish a tunnel with R3. Regardless who initiates it, R3 or R2, if they initiate it or try to set it up, they won't be successful because R2 is already at its limit. So the packets, because the tunnel isn't established between R2 and R3, the packets would all go through the hub and then down to R3. So let's try a basic ping. We'll do a ping out to 10.3.3.3. We'll source it from our 10.2.2 subnet. So even though the pings were successful, this syslog message indicates that, hey buddy, you are over your limit. You've had your capacity of IKE phase 1 tunnels. You can't set up anymore. I'm so sorry. You have been, says the router, denied. Now what's interesting is that if we did a trace route down to 10.3.3.3, we can see the literal path, and it should be, I'm expecting this path to go from R2 to R1, and then from R1 to R3. And there indeed is our path. So going through the hub, and then finally arriving at R3. Again, that last octet represents the router number. And because we're forwarding traffic to that destination, which in our routing table has 172.16.0.3 as the next hop, if we didn't already have that information cached in our NHRP table, we would do an NHRP request to resolve the NBMA address of 35003 associated with that next hop. That's off of our GRE interface. And then we would try to build an IKE phase 1 tunnel to negotiate with R3. And so we have that same message coming again saying, sorry, you're out of luck, you're over the limit. So we use the up arrow key a few times and do a show crypto ISACEMP SA. We've got our two tunnels in place, one between us and R1, the other is between us and R4. And I've got an idea. Let's do this. Let's go ahead and change the limit for IKE phase 1s with call admission control. Let's change it from 2, which is currently set at. Let's change it to a higher number like 6. To do that, we'll go into configuration mode and use the command crypto call admission limit IKE SA, and we'll use 6. We'll use the up arrow key a couple times, do a show crypto ISACEMP SA. Now we currently at the moment only have 2. However, if we start sending traffic over to R3, that's going to trigger the IKE phase 1 establishment between R2 and R3, and that will increase our security associations. So let's use the up arrow key a couple times. We'll do the trace route again, because that'll work. That'll send in-stream traffic. And check this out. Now if we do a show crypto ISACEMP SA, we now have these IKE phase 1 tunnels between R2 and R3. One that R2 initiated and one that R3 initiated. What I'd love to reinforce, however, is that these IKE phase 1 tunnels are not used for the actual transit traffic, like our ping and our customers' data. It's the actual IPsec security associations that are carrying transit traffic, like pings that we're trying to do, or Bob's traffic trying to get to a server on that subnet and so forth. So a moment ago, we were routing all the traffic through the hub, and then that hub was forwarding it over to R3. Now, because we have our security associations, both IKE phase 1 and the IPsec SA set up between R2 and R3, if we do that same trace route again to 10.3.3.3, sourcing it from our 10.2.2.2, that should have a direct shot straight to R3. And if we did a packet capture of that trace, we would see the packet being sourced from 25.0.0.2, destined to 35.0.0.3. In the IP header, it would point to the next protocol as protocol number 50, which is ESP. In the ESP header, it's got a security parameter index, it's got a sequence number, but as far as the actual payload is concerned, which has the original IP addresses involved, and the UDP that's being used by traceroute, all of that is completely hidden and encrypted by our IPsec that's being used for all of our GRE traffic. So in traceroute, there's actually 3 UDP segments all set with a time to live of 1. That original time to live in the traceroute is all buried and encrypted and hidden inside the ESP payload. And my guess would be that this would be the first of those 3. There's the second, and there's the third. And then when R3 received those requests, it decrypted them, it de-encapsulated them, looked at the actual payload, and then sent an ICMP message back with an unreachable message back to R2. And so these green ones would be the replies. And this little one right here is R2 talking to R1 about who knows what. It could be an EIGRP update that's being sent, or an EIGRP keep alive. It's really hard to say because we cannot see the details because they're all encrypted. I've also saved this capture file and I've placed it in the Nugget Lab files for you associated with this course. I have had a great time in this video. I'm so glad you joined me for it. Your action items are as follows. Number 1, I would strongly encourage you to practice, practice, practice. Everything we've done in this video, I'd like you to practice. Secondly, because it's really important to practice in a safe environment, I would recommend that if you haven't already, you might want to take a look at GNS3. And we have a course right here at CBT Nuggets on GNS3. Now the versions of GNS3, they may change and the interface may change slightly over time, but the basic functionality is the same. It's the ability to take a live iOS image and have it run in this GNS3 emulated environment where GNS3 is emulating the hardware, And then you have the real iOS that responds and acts just like real iOS would. The third thing I would encourage you to check out is Wireshark, and specifically the Wireshark course that we offer as part of the membership at CBT Nuggets. So again, thanks for joining me in this video on crypto call admission control. I hope this has been informative for you, and I'd like to thank you for viewing.